Hello, my name is Shahriar Shahriari, and this is a lecture in a series of lectures on introductory operations research based on my book, Linear Programming, Duality, and Games. The subject of this lecture is dictionary and tabulos. The idea of linear programming is to maximize or minimize a linear function, which we call the objective function, subject to linear constraints. In this lecture, I'm going to remind you how you use row reduction to solve a system of equations ax equals b. We will talk about what basic and non-basic variables are, what basic solutions and basic feasible solutions are, discuss briefly what linear programs in standard form are, and assuming that you have a given basic feasible solution, we will find an optimal basic feasible solution using the dictionary method and the tableau method. We will illustrate all of this through one example. In later videos, we're actually going to switch to the revised simplex algorithm and do everything via matrices and linear algebra. We have 4 equations and 4 unknowns, and you solve that using row reduction. If you don't know what that is, watch my videos on linear algebra where I go into much more detail. You write the augmented matrix. The entries are the coefficients of your variables. There's a row for every equation, and there's a column for every one of the variables, an extra column at the end for the right-hand side numbers. You find the reduced row echelon form of this matrix, another matrix that corresponds to a different system of linear equations that happens to be equivalent to this one, meaning that it will have exactly the same solutions. And the operations you are allowed to use are elementary row operations. There's 3 kinds of them: multiplying a row by a non-zero constant, switching the place of rows, and adding a multiple of a row to another row. And using those, you want to get the matrix in reduced row echelon form. That means there might be some rows of all zeros, and you want those to be at the bottom of your matrix. All the rows that are not all zeros, when you start on the left, the first non-zero thing you want to see is a 1, and that's called a leading 1 or a pivot. Every non-zero row should have a pivot or a leading 1, and those leading ones should be staggered from left to right as you come down. How you do that, pick a pivot first. For example, we pick that 1 at the top, and then we use that 1 to make everything else in that column 0 by multiplying that row by appropriate numbers, like for example, -2, and adding it to the second row, make that 2 into a 0. This is what you get. If we pick a second pivot, then we focus on this 3, and we want to make that a pivot. So the first thing we do is we multiply that row by 1/3 to make that into a leading 1. Now that it's a leading 1, we use that and make everything else in its column 0. We have a matrix in reduced row echelon form because all rows of zeros are at the bottom. Every other row, the rows that are not all zeros, have a leading 1, have a pivot, and the pivots are staggered from left to right. We started with this system of equations, and we found the augmented matrix and put it in reduced row echelon form. When we have a matrix in reduced row echelon form, then some of the variables are called basic variables. Those are the ones that in their column there is a leading 1, there is a pivot. If there's a pivot in your column, you're a basic variable. In this case, x and y are basic variables. And the other ones, the ones that do not have a leading 1, are called non-basic variables. This new augmented matrix, the reduced row echelon form of the original one, corresponds to a new system. That system is x minus w is -1 and y -2 is 0. There's only 2 equations because 2 of the rows are all just zeros. We have reduced solving that complicated system to this much simpler system. We let the non-basic variables be any real number that you would like. And then using those, you can find the basic variables. The basic variables appear only once in one of the equations, and their coefficient is a 1. So it's very easy to solve for them. For example, here, all you have to do is take w to the other side to find what x is, and you take 2z to the other side to find what y is. And w was an arbitrary number t, and z was an arbitrary number s, and because of that, I know what y and x are. So this gives all the solutions to that original system. There's one solution that we privilege, that we give a name to. If you put w and z equals 0, if you put all the non-basic variables equal to 0, then you get what we call a basic solution. In this case, you get y is also 0 and x is -1. This is the basic solution that corresponds to this choice of basic variables or non-basic variables. I could have switched the columns of this matrix. I could have decided that the order of the variables is not x, y, z, w, it's z, x, w, y. Based on that, I may have got other basic variables and other non-basic variables. It's not necessary for z and w to be non-basic and x and y to be basic. The basic solution is one that you get after you decide what the basic variables are and what the non-basic variables are. This particular one is a degenerate one because one of the basic variables ended up being 0 also. This will become important later on in our course. Now, let's start with a linear program. We are trying to maximize or minimize a linear function subject to linear constraints. The first thing that we want to do is we want to change this into something we call standard form of a linear program. The first thing we're going to do is we're going to turn those inequalities into equalities. Whatever solution that you find for this system, 4x1 plus 6x2 plus x3 better be less than or equal to 6. It might be 6, but it might be 5. It might be 5.3. And whatever it is, it's going to be off from 6 a little bit. I'm going to give a name to that. I'm going to call that x4. X4 is going to be that difference. If I add x4 to that, I will actually get an equality. I will do the same for the other two. I will add a variable, a slack variable, x5 and x6 to each one of those. What I will get is a different system that looks like this. I changed several things here. First of all, instead of maximization, I made it into a minimization problem. I want to do that always just to have a standard. So how do I do that? Instead of maximizing 7x1 plus 4x2 plus 2x3, I'm going to minimize minus 7x1 minus 4x2 minus 2x3. That will accomplish the same goal. Of course, at the end, when I find that this minimum value is going to be a negative one, and I remember that in my original problem, I wanted a maximization problem, and it was the negative of that. Let's look at the functionality constraints. The 4x1 plus 6x2 plus x3 less than or equal to 6 became 4x1 plus 6x2 plus x3 plus x4 equals 6. What's that x4? That's this new slack variable that I added to 4x1 plus 6 plus x3, which was supposed to be less than or equal to 6, to make it equal to 6. And I did the same for the other ones. This x4, x5, and x6 are all greater or equal to 0. So I have those signed constraints as well. Standard form, first of all, I want it to be a minimization problem. I want equality functionality constraints, not less than or equal to or greater or equal to. And I want all the signed constraints to be greater or equal to 0. Now, turning things to standard form, sometimes it's more complicated than you might think. This one was pretty straightforward, but there's other kinds of things that you can do. In a future video, we will talk about standard form in more detail. That was the original linear program. Here's the new one. This new one is in standard form, and these problems are equivalent in the sense that if I can solve one, I know the solution to the other. The second one is what's our standard form. It's a minimization problem, equality functionality constraints, and greater or equal to 0 sign constraints. I need to have all those three to have something in standard form. I said our standard form because some authors will have different kinds of standard form. It's just a matter of picking one form that you're going to call your standard form and then working your way through that. A linear program is going to be, for us, any optimization problem that's equivalent to one in standard form. If you come up with any optimization problem, and you can find a standard form linear program that is equivalent to it, meaning that by solving it, you can solve your problem, then that thing that you started with, we're going to call linear program. That's going to be our working definition of what a linear program is. Our goal is to understand the simplex method, which is the method for solving linear programs. And to understand it, you want to do some small examples by hand. In real life problems, you're going to use software to solve the simplex methods for you. But before using it as a black box, you want to do some by hand to see what kinds of things can happen, what things can go wrong, what's happening under the hood of your method. And the common approach for that is something called tabulos. And I will tell you what those are. But Vasek Shvatal has something called dictionary method. And shout out to his great book, Linear Programming, that explains how tabulos work really well. We're going to go through dictionaries to understand exactly how we're going to approach an optimal solution. Then I will tell you how that translates to tabulos. In this set of lectures, but not in this particular lecture today, we're actually not going to use tabulos or dictionaries. We're going to use the revised simplex method that uses matrices and linear algebra. That's the method that most software programs use. And also, it's one that's more adept in proving things. It's easier and cleaner to prove things using linear algebra than without it. When LP is in standard form, we can find basic and non-basic variables. It's not the case that if you have an LP in standard form, the basic and non-basic variables are staring you in the face. You might have to do elementary row operations to find such things. But you can, because it's a system of linear equations, you can find basic and non-basic variables, and you can find basic and basic feasible solutions. Basic feasible solution is one where not only is a basic solution, but also it's feasible in the sense that it satisfies the sign constraints. The starting point is that given that you have a basic feasible solution, you can write something called a dictionary for it. What the dictionary is gives you the basic variables and objective function in terms of the non-basic variables. So that's why it's called a dictionary. Here's the objective function, here's this basic variable, here's this definition. And the definition is going to be in terms of the non-basic variables. Our Alpine standard form was this guy. In this particular case, we know exactly what our original BFS is. X4, X5, and X6 are basic variables. X1, X2, and X3 are non-basic variables. And the basic solution is also feasible. So x1 equals 0, x2 equals 0, x3 equals 0 are the non-basic variables. You put them equal to 0, and you get that x4, x5, and x6 are 6, 12, and 9, and z is going to be 0. This is the basic solution because we put the non-basic variables equal to 0 and got the basic variables. If you do that, you might not get a feasible solution in the sense that it might be that not all your sign constraints are satisfied. But if they are, then you have a basic feasible solution. It will be one of our tasks to figure out how to get that starting basic feasible solution. But right now, we're assuming that we are starting with an Alpine standard form where we have some basic feasible solution and we want to know what to do with that. So our first dictionary, as I said, we want to write the objective function and the basic variables in terms of the non-basic variables. The objective function is already written in terms of the non-basic variables, but the other guys, x4, x5, and x6, we solve for them. We now have a dictionary that tells us exactly what the basic variables and the objective function are in terms of the non-basic variables. Again, we have this basic feasible solution and we have this dictionary corresponding to it. I wanted to minimize z, but I managed to make z 0. Can I do better than that? By swapping a non-basic variable for a basic variable and switching their place. Right now, the basic variables are x4, x5, and x6. Those were my slack variables. The question is, which variable do I want to enter the basis? I will choose the one that has the most effect on z. I want to minimize z. I want to make z small, and right now it's at 0. If I look at my objective function, I will see that x1 has that coefficient of -7, so it gives us a bigger bang. If I can increase x1 from 0, that's the one that's going to give us the bigger bang, and we're going to get a smaller z. So x1 should be the one that enters. Now, if x1 enters and becomes a basic variable, one of the current basic variables needs to become non-basic. Which one of them should leave the basis? I want to make x1 as large as possible. See which one of the other ones are in the way of making x1 as large as possible, and that will help us figuring out the variable that leaves. Here was our dictionary 1, and x1 was to enter the basis. x2 and x3 are going to stay non-basic, so they're still 0. And so x4, x5, or x6 are going to leave. How am I going to decide that? I'm going to try to make x1 as large as possible. Could I make x1 100? That would make z -700. That's pretty good. I couldn't do that because if you look at the next equation, x2 and x3 are 0. If you make x1 100, x4 becomes negative, and that's not allowed. In fact, x5 and x6 also become negative. So I can't make it that large. Can I make it 1? And the answer is yes, I can, because again, x2 and x3 are 0. 6 minus 4 is 2, 12 minus 6 is 6, 9 minus 4 is 5. That's a solution that's possible. So it's possible to make x1 as big as 1, but I want to make it as large as possible. I need x4 to be greater or equal to 0. That means that 6 minus 4x1 got to be greater or equal to 0, and that tells me that x1 can't be any bigger than 3/2. But 12 minus 6x1 got to be also greater or equal to 0. That gives me x1 less than or equal to 2. And the final one, 9 minus 4x1 being greater or equal to 0, gives me x1 is less than or equal to 9/4. All three of these have to be the case. x1 has to be less than or equal to 3/2, less than or equal to 2, and less than or equal to 9/4. The most restrictive one of those is 3/2. So x1, that's the best I can do. 3/2. When I do x1 3/2, I see that first equation is going to give me that x4 is going to be 0. So x4 is the one that's going to leave. x1 enters, and x4 is going to be the variable that leaves the basis. In this new regime, x2, x3, and x4 are 0. x2 and x3 were non-basic to begin with, and now x4 has joined them. And x1 is 3/2, and by putting x2, x3, and x1 there, I know what x5 and x6 is, and I've got myself a new basic feasible solution. So this is my new BFS. And as soon as you have a new BFS, you can have a new dictionary, or you must have a new dictionary, because you want to write again the objective function and the basic variables in terms of non-basic variables. So we have to change our dictionary. This was our first dictionary, but now we have a new BFS, and we can find the objective function. It has improved. It's gone from 0 to -21/2. Remember, we want to minimize it. The question is that, can we do better? If you look at my objective function, we increased x1 from 0. We might say, well, let's increase x2. But I can't really decide what am I going to exactly do without a new dictionary. I need z, x1, x5, and x6 in terms of x2, x3, and x4. I'm going to solve for entering in terms of leaving. Look at this equation. x4 equals 6 minus 4x1 minus 6x2 minus x3. I have an entering variable x1. I have a leaving variable x4. In that equation, I'm going to solve for x1. And I will get that x1 is 3 halves minus 3 halves x2 minus 1/4 x3 minus 1/4 x4. This one is good because it's telling me x1, one of the basic variables in terms of non-basic variables. But the other ones, even though the non-basic variables are over here, I have x1s here, and I don't want any basic variables on the right-hand side. What I will do is that I will substitute this equation in the others. The new BFS again is this, and I have x1 equals 3 halves minus 3 halves x2 minus 1/4 x3 minus 1/4 x4. I will substitute that in all the other ones, and this is messy, just a lot of algebra. That's the advantage of the Tableau method, that elementary row operations will do this substitution for you. This is what you get. Notice that on the right-hand side, I have only non-basic variables. I don't have any x1s here anymore. On this side, I have z, x1, x5, and x6. Looking at this, z right now is minus 21 halves because x2, x3, and x4 are 0. And I want to make it smaller. The only way to make it smaller is by making x3 go up. Not x2, but x3. If you increase x2, z will actually go up. And that's not what you want. So you want x3 to enter. How big can I make it? x2 and x4 continue to be 0. In this equation, I need 3 halves minus 1/4 x3, which is x1, to be greater or equal to 0. And that gives me a condition. x3 is less than or equal to 6. The next one actually gives me a condition that I don't have to worry about. It tells me that x3 has to be greater or equal to minus 6. That's actually a point because this coefficient of x3 here was positive. And if that's the case, then that's not going to put any constraints on x3. The last one tells me that x3 got to be less than or equal to 3 halves. So I know that 3 halves is my most restrictive thing. So x3 got to be 3 halves. If I put 3 halves here, then x6 is going to become 0. That's going to be the leaving variable. My dictionary 2 was this guy, x3 enters, x6 leaves, and I have a new BFS. This time, x2, x4, and x6 are 0, and because x6 now left the basic variables, became non-basic, and x3 is 3 halves, x1 is 9/8, and x5 is 15/4. And z is minus 87/8, so we have improved it. Can we do better? The same question as before. And again, we need a new dictionary. I need basics in terms of non-basics. I need this time z, x1, x3, and x5 in terms of x2, x4, and x6. And I will again solve for entering in terms of leaving. x3 was entering, x6 was leaving. There's an equation that will tell you what x3 is in terms of x6. And that's this last equation here. If you solve for x3, you will get, assuming all along that I have not made an arithmetic mistake, which I may have, is 3 halves minus x2 plus 1/2 x4 minus 1/2 x6. And you need to substitute in the others. Here's our dictionary 2, and x3 enters, x6 leaves, and this is what we're going to substitute in. You should substitute in all of them, but the best thing to do is first to substitute into objective function. When you do that, you get this as your objective function. Minus 87x plus 27/4 x2 plus 13/8 x4 plus 1/8 x6. And right away, we see we can't do any better because all these coefficients of x2, x4, and x6 are positive. If you make any of x2, x4, and x6 anything other than 0, make them positive, then your z will actually increase. And we were trying to minimize z. Because those coefficients, not the constant term, but the coefficients of the non-basic variables are positive, we can't improve z anymore. We have found that our current BFS is optimal. So optimal solution is z equals minus 87/8, and the non-basics are x2, x4, and x6, and the basics are x3, x1, and x5. If we go back to our original maximization problem, now we have found that the maximum value is 87/8, and x1 is 9/8, x2 is 0, x3 is 3 halves. The x4, x5, and x6 were things that we had introduced, and we really didn't care about them to begin with. We do know that this solution is optimal because of the dictionary told us that there's just no way to make this any better. We have actually proved that we have the optimal solution. But we don't know if this method always works. We applied it to a very specific kind of a problem, and so it's not clear that it would work always. One particular thing is that we started by an initial basic feasible solution. It's not clear how you can always do that. We need a proof that this method always works. Those are things that we will do using the revised simplex algorithm and linear algebra. Now switching to Tableau's, same problem, but I'm starting with the standard form. I want to minimize z subject to some constraints, but I've made a slight change. This is in standard form, but I put the objective function as my last equation, and I put z as the last variable. I brought everything to one side. That's why all these guys are positive now. This is 4 equations of 7 unknowns, and I know how to solve those using reduced row echelon form. I want a solution that has the smallest value for z and non-negative values for the rest. I will write the augmented matrix, and I will try to solve it, but I will decide how to do pivots judiciously. Our first tableau is this. This is my equations, 4x1 plus 6x2 plus x3 plus x4 equals 6. My objective function ended up being here, 7x1 plus 4x2 plus 2x3 plus z equals 0. Those first 3 are my constraints, and the last one is really the objective function that became a constraint. Columns with a pivot are basic variables. Column that has a pivot, a 1, and zeros everywhere else like these. This is in reduced echelon form, give or take the fact that the columns need to be reordered. I need to bring x4, x5, and x6 at the beginning to make this in reduced echelon form. If I do that, then x4, x5, and x6 will have leading ones, which are the pivots, and those are the basic variables. But I'm not going to move them there. I'm going to just keep them here. I'm going to go with the fact that these guys have these pivots in them, and so they're the basic variables. The basic feasible solution for this is that x1, x2, x3, the non-basic variables are 0, x4, x5, and x6 are 6, 12, and 9, and z is 0. As I go to the tableaus method, you should stop the video and go back to the dictionary method and see that these two methods are exactly the same. It's just that the tableau method is a more streamlined version, but it's less clear why am I doing everything. The dictionary method makes you think through exactly why you're doing every step. But here you try to turn it into an algorithm that's quicker to do, but with less understanding, more like a computer. I need to decide what the entering and leaving variables is, and that's the same as finding a new pivot. For example, if I decide that this 3 is the one that I'm going to make into a 1, then this 1 over here is not going to be a pivot anymore. Then I've decided that x3 is going to enter and x6 is going to leave if I do that. How am I going to do that? First, I will look at the bottom here, and 7 is the largest positive in the last row, and that's the one to enter. Remember, in the dictionary method, we took the one that was the most negative, but because we have moved everything to the side, they're now positive. x1 is to enter, so something in this column is going to become a leading one. Depending on which one it is, that decides which one is going to leave. That's the place where we decide how large x1 could be and what the constraints are. We looked at various ratios and decided which one is the most restrictive. If you think back exactly what we did, what we have to do is ignore zeros or negative entries. Those correspond to constraints that actually do not give you a constraint. Something like x1 got to be greater or equal to -6. If there is any zeros or negatives here, you just ignore them. For all the other ones, you find the smallest non-negative ratio of the column of B divided by column of x1. So what does that mean? You take 6 divided by 4, 12 divided by 6, and 9 divided by 4. You look at them and see which one is the smallest non-negative one, and that's 6 over 4. So the pivot is going to be around 1, 1. Which means that x1 is entering, but x4, the one that used to have the pivot in that row, is the one that's going to be leaving. So x4 is going to be the leaving variable. Here was my tableau, and I've decided what my new pivot is. I divide that by 4, make it into a 1, and then use that to make everything else in its column 0. When I do that, I get this new guy. And now I have new basic variables and new non-basic variables. Here it is. The new basic variables are x1, x5, and x6. The new BFS is x2, x3, x4. The non-basic variable is 0, and the other ones you can just read off from the B exactly what they are, and we know what our objective function is. Again, I look in here and see that 1/4 is the largest positive in the last row. I'm not going to worry about z itself. Z is going to stay. Among the variables, the largest possible coefficient is 1/4, so x3 is to enter. I have to decide where is the pivot going to be. In that column, I'm going to ignore zeros and negatives, and there's actually a negative. I'm going to ignore that, and I'm going to look at the smallest non-negative ratio of column B divided by column of x3. So 3/2 divided by 1/4 and 3 divided by 2. That's 6 versus 3/2. So 3/2 is the smallest one. That tells me I want to pivot around the 3, 3 entry. And then that tells me that this x6 is going to be the one that's leaving. So I now know that I want x3 to enter and x6 to leave. And the way I do that by pivoting around 3, 3. Here's my second tableau. I go to that guy and I make that into a 1, and then I use that 1 to make everything else in its column 0. If you do that, you get a new tableau, and here's what you get. This time when you look at these coefficients, you see that they're all negative, and therefore you already have your optimal solution. Here was our third tableau. The new BFS is x1 is 9/8, x3 is 3/2, x5 is 15/4, and x2, x4, and x6 are non-basic variables. They're 0, and z is minus 87/8. There's no positive entries as the coefficient of variables in the last row. That tells me that this is optimal. Again, the Tableau method is exactly the same as the dictionary method, but it's more streamlined because you don't have to do algebra. All you do is elementary row operations. This is the end of this lecture. Like my video if you like it. Subscribe to my channel if you want to be subjected to math videos on your feed, and keep hydrated at all times.